Okay, so 16.3, graphs of functions. We're going to go over 4 concepts. The first concept is linear and constant functions, and then graphs of basic functions, and then definitions of a quadratic function, and then finding the x and y intercepts. So we're going over a little of all the functions today. So concept 1, linear and constant functions. So let m and b represent real numbers such that m is not equal to 0. Then a function can be written as f of x is equal to mx plus b, which is a linear function. You just need to know this part. F of x is equal to mx plus b is a linear function. A function can also be written in the form f of x is equal to b, which is a constant function. So we have a linear function and a constant function. And remember, instead of f of x, we could always write y. So this is y equals mx plus b, and y is equal to b. Okay. Remember, this b is just a number. If we're looking at a linear function, this m represents the slope, and this b represents the y-intercept. So in a constant function, we only have y equal to the y-intercept, which would result in a horizontal line. We're going to see that here on the examples. So linear and constant functions. So looking at the first 2 graphs, the first graph we can say is a linear function because it is in a line, right? And it doesn't matter if that line is going in the positive direction, the negative direction. As long as it forms a line, it is a linear function. For the second graph, we have a constant function since it gave us a horizontal line. So for this function, f of x is equal to 3. This 3 is the y-intercept. So notice that it crossed right here at 3, but since it did not have a slope, we just drew a horizontal line through it. Both of these graphs are under linear functions. So a constant function can be considered a linear function, but the opposite is not true. So this first graph we couldn't say is a constant function, okay, because a constant function is only in that horizontal line. But both of these graphs can represent a linear function since they both are straight lines, okay. One is tilting to the right, and one is just horizontal. Okay. Start at these ones. Concept 2 is graphs of basic functions. Okay. So we're going to look at 6 basic functions and their graphs. What the most important part to remember here is when we identify a function, to remember what the graph looks like in general, okay? And it is helpful to also memorize the domain and ranges of those graphs. So when you look at them, you're not having to use the concept like last time and analyze the graph. You could just be able to say, okay, this is linear. I know a domain and range of a linear function is all real numbers. Okay, so let's look at these functions. The first function we have here is the identity function. The identity function is a linear function. The reason it's called the identity function is because this f of x is equal to x, so y is equal to x. This is just the parent function of all linear functions since this is going through the origin. It's also considered the identity function because we do not have a b value. So this y equals x is technically y equals x plus 0 because there is no intercept here besides through the origin at that 0. Okay. So again, this one is just a line. The second type of function we're going to talk about is a quadratic function. So the parent function for a quadratic function is f of x is equal to x squared. So y is equal to x squared. Okay. When I say parent function, I just mean the basic, like the most basic you can write that function. Okay. When we're dealing with problems that are linear or quadratic, you'll see other numbers attached to this, okay? That is going to change our graphs to either be, let's say, upside down, off to the right, up higher. Those are our child functions that are all changing, okay? And we're going to talk about that in a couple more notes. So right now we're just looking at the most basic of the functions. So we have identity function, which is the linear function, quadratic function, and then we have the cubic function. It's called the cubic function because if we look at the parent function of it, it is f of x is equal to x cubed. Or we could write this as y equal to x cubed. The cubic function is always going to look like this curve, okay? It's always going to have a arrow going in opposite directions. So it could look like this, up or down. It could also look like this. And then, of course, it could look like any of these ways, but transformed onto the graph, so moved around on the graph, okay? So again, the important part of this section is that if you were given all of these graphs, are you able to label them? Are you able to say that's a cubic function? Okay. Next is the absolute value function. The absolute value function is f of x is equal to the absolute value of x, or we could write this as y is equal to the absolute value of x. One way to identify this function easy is when you look at the vertex or the point that is in the center, this forms a V. So it's a V shape. Okay. The only function that forms a V like that is the absolute value function. So when we looked at the quadratic function formed that U at the vertex. It's a U shape. All quadratic functions form that U shape, just like all absolute value functions form that V shape. The next function we're going to look at is the square root function. The square root function is represented by f of x is equal to the square root of x, or we could write that as y is equal to the square root of x. When we see the square root function, it's always going to look like, imagine it like half of a quadratic, right? Because we could finish that off here and make it the rest a quadratic, but it's only half of it. So it could go in this direction, it could go in the other direction, it could go in this direction, okay? Depending on what is added to that parent function is going to determine which way it goes. But it's always going to have this shape, okay? It's always going to look like it's a quadratic function cut in half. And then the last function here is the reciprocal function. The reciprocal function is represented by f of x is equal to 1 over x. So reciprocal function, just think fraction. Fraction, that includes the variable. could be written as y is equal to 1 over x. Okay. With the reciprocal function, you're always going to have what looks like, let's see, what looks like almost the quadratic function, but it's going to be two of them going in opposite directions. So we could see one that's looking like this in these directions. It could be represented in these directions. As long as there are two curves on that graph, it is a reciprocal function. So again, these are the 6 main functions we're going to be looking at. You just need to be able to identify them. Any questions? Okay. Okay, on the first 2 examples, we are going to be using that function notation that we learned in 16.2. We're going to be plugging in x values that we choose to get corresponding y values. And we're going to use those values to create points to plot on a graph. Okay? Once we plot these functions on a graph, you're going to tell me what this function is. Is it linear, quadratic, cubic, so on and so forth? Okay. When we are creating our table, does it matter which x values we choose?
Yes.
So yes and no. So it doesn't matter specifically which numbers, but it does matter that you include some negatives and some positives. So the numbers that I like to choose are -2, -1, 0, 1, 2. So those are the numbers that I'm going to use every single time. But again, as long as some of your numbers are negative and some are positive, it does not matter which x's you choose. Okay? So remember, in function notation, we take these numbers and we plug it in for x. So for -2, we have f of -2, which means -2 squared, since our function is x squared. So f of -2 is equal to 4. So that first value is 4. And we're going to do that for every single value. So f of -1 is equal to -1 squared. So that means f of -1 is 1. Okay. Then we're going to do f of 0 is equal to 0 squared. F of 0 is 0. F of 1 is 1 squared. So f of 1 is 1. And f of 2 is 2 squared, so f of 2 is 4. Why were my values for my negative numbers the same as my values for my positive numbers?
You're squaring them.
Good, you're squaring them. And so when we square negative, it becomes positive, and when you square a positive, it remains positive. Okay? Didn't leave much room to plot this. So now we're going to, let me see. I wrote this way too big. Can I move this? Yeah. I'm going to create a graph. Next time I'm going to write a lot smaller. And I'm going to plot these points. So remember, these points can be written as x comma y. And that's what this f of x is. This is our y. So our first point would be -2 comma 4. So -2, 4. And I'm just sketching out this graph. Then I would have -1, 1. Then 0, 0. Then 1, 1. And 2, 4. So looking at this graph, if I was to trace this, I have what type of function? Quadratic. Okay, so I have a quadratic. Okay. And obviously we know that because if we look at the beginning, we had that f of x is equal to x squared, okay? So we could have just looked back at our chart and was like, okay, this is quadratic. But in some cases, you're not going to be given the function. You might just be given the points on the table. And you're going to have to determine what type of graph it is. Okay. So looking at number 2, this f of x is equal to negative x squared. Right away we know this is what type of function? Quadratic. And what do you think that negative is going to do to it?
It's going to go negative, or in the negative direction.
Good, it's going to turn upside down. Okay, so we're going to show that by plugging in our same x values. So we're plugging in our negative 2, negative 1, 0, 1, and 2. Okay, so plugging in negative 2, I have negative 2 squared, which is negative 4. Okay, and I'm going to be doing this for each one. So plugging in negative 1, I get negative 1. Plugging in 0, get 0. Get negative 1 again. And then plugging in 2, I'm also going to get that negative 4. Okay. These all ended up negative because of that negative outside of the x squared. So if I was to graph this, I have negative 2, negative 4, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 4. So I have my quadratic, but facing in the other direction. Okay, so this is quadratic. But that negative here turned it upside down. Any questions on 1 or 2? Okay, we're going to do the same for 3 and 4. Just looking at the function for 3, we know this is what type of graph? Reciprocal because of that 1 over x fraction. And then what about number 4? Right away we know this is what type of graph? Absolute value because of that absolute value symbol. So again, I'm going to do the same thing. I'm going to be plugging in my same numbers, negative 2, negative 1, 0, 1, 2, in for my function of 1 over x. So f of negative 2 gives me 1 over negative 2, which is negative 1/2. Same with that negative 1, I get 1 over negative 1, which gives me negative 1. F of 0 is equal to 1 over 0. What is 1 over 0? Is it 0 or it does not exist?
Does not exist.
Does not exist. You cannot divide by 0, so this does not exist. What does that mean here for this point? Is it going to be part of our graph? No, so this is not part of our graph. Okay, so f of 1, we get 1 over 1, which is 1, and f of 2, 1 over 2, which is 1/2. Okay. Remember, when I'm graphing, it's better to have my fractions as decimals. So what is 1/2 as a decimal? 0.5. So first graphing that negative 2, negative 0.5. Say that's right here. Again, this is just a sketch. I should actually, there we go. Negative 1, negative 1. Okay, and then 1, 1. And then 2 1/2. Okay. If we did not know what this function was, we would not know how to use those points, right? But since we know this is going to be a reciprocal function, we know that we're going to have a graph that goes off of the first quadrant and a graph that goes off the third quadrant. So it's going to look something like this and like this. Okay. Obviously, if we would have tried more points, so let's say larger numbers than the 2 and the -2, we would have had more points on this blue graph that I drew. But we know that 1 over x is going to be our reciprocal function. Okay. Then last example for this concept, we have our absolute value function. What do you think that -1 is going to do to our function?
Lower it down 1.
Good, lower it down 1. So let's see if that is true. So we're going to pick our numbers. And then actually, let me bring you back to 3 because I forgot to show you this. So remember when we got that did not exist for 0? Notice how there's no points right here for 0. Okay, so I'm going to go ahead and plug in my numbers. Remember, what does that absolute value sign do? Good, makes any number positive. So if we have a -2 inside of it, it's going to be a +2. If we have a positive number, it's just going to stay positive. So f of -2 is equal to the absolute value of -2 minus 1, which is 2 minus 1, which is 1. F of -1 is equal to the absolute value of -1 minus 1, which gives us 1 minus 1, which is 0. F of 0 is equal to the absolute value of 0 minus 1. What's the absolute value of 0? 0. Good. So we get 0 minus 1, which is -1. F of 1 is equal to the absolute value of 1 minus 1, which is still 1 minus 1, which gives us 0. And then lastly, f of 2 is equal to the absolute value of 2 minus 1, which gives us 1. Okay. So if we were drawing our graph, we have our first point of -2, 1. So -2, 1 right here. -1, 0. 0, -1. 1, 0. And 2, 1. Okay. Since this is an absolute value function, what is my vertex or my end point going to look like? A U or a V? A V. Okay, it's very important because if we make it look like a U shape, then I'm going to assume it's a quadratic and not an absolute value. So notice here that this absolute value did decrease by 1, because if we remember our parent function, so our parent function up here, where was this vertex, this center V shape? At what point? 0. It was at 0, the origin. And then when we graphed it, since they added that -1 to the end, our absolute value function went down 1. So it's no longer at the origin, now it's at -1. Okay. Any questions about concept 2? Okay. Concept 3 is the definition of a quadratic function. A quadratic function is defined by, this is what's important here, f of x is equal to ax squared plus bx plus c, where a, b, and c are all real numbers and a cannot be 0. Why do you think this information is important here? A cannot be 0. What would happen if this a value right here was 0? What would happen to the x squared?
It would become 0 and then become a linear equation.
Correct. This whole thing would cancel out, right? So then we would just be left with bx plus c, which is a linear equation and not a quadratic. That's why the a value is not equal to 0. And then this information here is just telling you that our a, b, and c in this function are not variables, but instead numbers. Okay, and they can be any numbers as long as they are real. Okay. So we know that a cannot be 0, but what happens if a is positive? So when a is positive, our quadratic, which is also called a parabola, opens in what direction? Up or down? Up. So our parabola, again, another name for quadratic, opens up. And what I mean by that is that when we're looking at our vertex, and our function where the arrows are, our parabola opening up means our arrows are going in the positive direction. So that means when our a is negative or less than 0, which way is it going to open? Good, down. So our parabola opens down. And again, this center point here, where the curve changes on our quadratics, is called the vertex. Okay. So again, this is just defining a quadratic function, explaining what it looks like if our values of a changes, so the number before x squared. So on these examples, let's see, I want you to tell me if they are, and I forgot to write that instruction here, so are they linear, quadratic, constant, or neither? Okay, so they're 1 through 9. They're either linear, quadratic, constant, or none of the above. So looking at number 1, we have f of x is equal to -4. What type of function is this? Constant. So the reason it's constant is because we don't have a variable there. We don't see a variable. Okay. What about number 2? F of x is equal to x squared plus 3x plus 2. Quadratic, and how do we know?
X squared.
Good, we know because of that x squared. What about f of x is equal to 7 minus 2x?
Linear?
It's linear, but is this written in the correct form?
No.
No. What should come first?
The -2x.
The -2x. So technically this is f of x is equal to -2x plus 7. And then we know this is linear because of the variable x. Number 4, we have f of x is equal to 4x plus 8 over x. What type of function? It's still linear. Good. Why is it still linear?
4x.
Good, because we could take that divide by 8, right? And we could simplify this. We could write this as 4x over 8 plus 8 over 8, which simplifies to 1/2 x plus 1. We know right away that that 1/2 x plus 1 is linear. It's easier to see that way than it is to see in that fraction. The only way this would be considered a different function is if the x was where?
The denominator.
The denominator. Linear, and I'm going to say x was in the numerator. So knowing what we just found out on 4, number 5 would be considered what? So first, is it linear, quadratic, constant, or neither?
Neither.
It's neither because what is it? Reciprocal. Good. And we know it's reciprocal because the x is where? Denominator. Perfect. Okay, so that was 1 through 5. Number 6, what type of function?
Quadratic.
Quadratic. And how do we know?
X squared.
Good, the x squared. Number 7, n of x is equal to -6 is what type of function? Everyone agree? Constant? Why is it a constant function?
There's no variable.
There's no variable. What about number 8? What type of function?
Linear.
Linear, good. Because of that one variable, x. Okay, and what about number 9?
Neither.
Good, it's neither, because what is it?
Reciprocal.
Reciprocal. And how do we know it's a reciprocal function?
The denominator.
X is in the denominator. Okay. So again, in these examples, we were just identifying what type of functions they are. Any questions on 1 through 9? Okay. The next concept here is finding the x and y intercepts of a graph defined by y is equal to f of x. Okay. When we see y is equal to f of x, typically it's talking about linear equations. So we're finding the x and y intercept of linear equations. So in this definition, it says given a function defined by y is equal to f of x, the x-intercepts are the real solutions to the equation if our function is equal to 0. And the y-intercept is given by f of 0. So another way to write this, it's saying that the x-intercepts is when y equals 0. And the y-intercepts is when x equals 0. So think the opposite. So if we need to find the x-intercepts, we need to plug in 0 for x-intercepts. For y. If we need to find the y-intercepts, we need to plug in 0 for x. Okay? This is the shortcut version of what this just said. Okay, number 1, we have f of x is equal to 2x minus 4. This is what type of function? Linear. So it wants us to find the x-intercepts. So we know that we're plugging in 0 in for y. And in this case, we don't see a y, but we know y is what? F of x. So this is y is equal to 2x minus 4. We are plugging in a 0 in for y and solving for x. So what would be our first step?
Add the 4.
Add the 4, good. So we have 4 is equal to 2x. Last step,
Divide by 2.
divide by 2, and that tells us that x is equal to what?
2.
2. If we're finding intercepts, would this be our answer, or would we have to write it a different way?
2 comma 0.
Correct. We would have to write it as a point, 2 comma 0, because we're talking about graphs. This x equals 2 tells us nothing, but this 2 comma 0 tells us a point on the graph that is the x-intercept. So this is our answer. Okay. The rest of number 1 is on the next page, so right here. Part B says find the y-intercept. So that means we're going to plug in 0 for what? So f of 0 is equal to 2 times 0 minus 4. So f of 0 is equal to 0 minus 4, which gives us what number? Negative 4. And what's our point?
0 comma negative 4.
0, negative 4. Okay. Now that we have the x-intercept and the y-intercept, we can graph our function. Okay. So instead of creating a table to graph our function like we did in the beginning, we can use these 2 points that we found, plot them on a graph, and connect the points to form our linear graph. Okay, so here is my function. I'm going to first graph 2 comma 0. So 1, 2 right here. Then I'm going to graph 0, negative 4 right here. So when I connect my points, do I connect it like this? Yes or no?
Yes.
No, we don't connect it like this because this is telling us we have restrictions, right? We're just plotting an entire graph, so that means we have to draw in both directions an arrow. Okay. So on an exam, if you do not continue your graph when you draw it with the arrows on either side, and you just connect the 2 points, that will be wrong. You have to draw the entire graph. Looking at this graph, is this a positive or negative graph? Positive, and how do we know? Good, because it's going towards the positive direction of the x's, okay? We also know it's positive because if we look at the number before x, is that positive or negative? That 2. It's positive, so that 2 in front of our x determines the slope. And right here we can tell that our slope is positive. Okay. Go ahead and try number 2. Number 2, we have f of x is equal to negative 5x plus 1. So find the x-intercepts, find the y-intercept, and then we'll do them together and graph. Okay, so follow the same method as number 1. In the first one, you are going to get a fraction, okay? Just make sure we turn that fraction into a decimal because we're going to make it into a point. Okay, so finding the x-intercept, we have 0 plugged in for y, so that gives us 0 is equal to negative 5x plus 1. What would be our first step? Good, subtract 1. We get negative 1 is equal to negative 5x. Last step, divide by negative 5. So we get x is equal to positive 1/5, which is approximately what in decimal form?
0.2.
Is it point two? Okay. So how would we write this as a point?
2,0.
Good, 0.2, 0. And why are we turning it into a decimal? It's easier to graph, easier to plot on our coordinate plane. And then for the y-intercept, we plug in 0 in for x. So we have f of 0 is equal to negative 5 times 0 plus 1. Negative 5 times 0 is 0, so we have 0 plus 1, which is 1. And that gives us what point? 0, 1. So then plotting this, first plotting that point to 0, and then that 0, 1. Again, I'm not just connecting those two dots, I am drawing a linear graph through those dots. And then looking here, I could tell my slope is what, positive or negative? Negative. And I could also tell that from what?
Negative 5x.
Good. That negative 5 in front of the x tells us the slope. So it's a negative slope. Okay. So this is x and y intercepts from a linear function. Okay. We could also find x and y intercepts from different types of functions. So looking at 3 and 4. Okay. 3 and 4 are, like we didn't talk about what the function is for 3 or what the function is so much for 4. All we need to know here is since we are given the graphs, we're just finding the x and y intercepts based off the graph, okay? So for part A, it says find the real values of x for which f of x is equal to 0. So what is it asking us to find?
X-intercept.
Good, the x-intercepts. And we know that we can find the x-intercepts by finding where the graph crosses where? Good, the x-axis right here. So for A, we're seeing where this graph, where this blue line is going to cross my blue line. Okay, so looking at this, how many x-intercepts do we have?
3.
We have 3. So we have one here, here, and here. What are those points? Left to right.
-2, 2, 3.
Good, so writing them as points, -2, 0. What's the next one?
2, 0, 2, 0.
2, 0, 3, 0. These are our x-intercepts. So in part A, if they wanted us to find the x-intercepts, what do you think they're asking for when they say find the value of f of 0 in part B? What? The y-intercepts. Okay, so now we're finding the y-intercepts, and that is when the graph crosses which axis?
Y.
The y. So how many y-intercepts are there? 1, good. And that is going to be what point?
0,
Good, 0, 6. Okay. So go ahead and take a moment, do number 4. Find the x-intercepts and find the y-intercepts and write them as a point. Okay, so for part A, how many x-intercepts did you find? 3. So at -2, 1, and 4. So those points should have been -2, 0, 1, 0, and 4, 0. How many y-intercepts? 1, and at what point?
0, 4.
Good. 0, 4.